CNS logo.
Yeah, it is kind of a cool logo. All right. So today I don't have a a presentation put together over something related to RDMA or whatever. So instead, I'm going to talk about some of the work that I've been doing on Corundum over the past couple of weeks, because this kind of dovetails with, kind of the future direction that I have in mind for Corundum. So I apologize in advance for breaking everybody's customizations of Corundum, but with this new setup, it's going to be hopefully a lot more flexible and a lot more extensible going forward. All right. So I got a bunch of stuff that I'm going to talk about today. Most of the stuff I'm just going to be pretty brief, but if anybody has any questions, we can go as deep as you want. Okay, so let's see. A lot of the stuff is kind of in the weeds, but yeah. So one of the kind of general goal that I have is in terms of simplifying the core logic and removing duplicate functionality, and making things easier to modify, easier to adjust. So one issue that I ran into is that on each of the boards there's a huge amount of duplication, but there is a small amount that's different between the boards, and this mainly has to do with the control registers. So I had to come up with a better way of kind of implementing control registers in order to do anything else, really. So that was the first thing that I did. So I'm going to talk about that a little bit. And then I put the scheduler in its own kind of block. That'll make that easy to swap out, because the previous setup, we had like some Verilog parameters that's, brought in a couple of additional modules under certain conditions. So now we have a separate block that you can swap out. So we have one for a normal round robin scheduler and one for a TDMA scheduler, similar to how the application section is going to work. And then I did some rearranging of the register space to make things a little bit more efficient in terms of utilization. And then I've been pulling out the shared logic into a common, set of modules that eventually all the targets are going to use. I've been working on some TCL-based reconfiguration, or some TCL scripts that are going to be used to configure kind of the top level of the design, including, the PCI Express IP cores and whatnot. So that's going to be super useful. And then over the past few days, I got the statistics counting subsystem working. Mainly right now that looks at PCI Express counters, but eventually we're going to extend that to look at all sorts of stuff. And then the thing that I'm working on next is actually integrating the, at least first version of the application block. Once all that's done, then I'm going to update all the target designs, rebuild everything, make sure they all close timing and whatnot, and then we'll push that to the main Corundum repository. Hopefully that'll happen sometime this week. And then I have some benchmarking measurements for PCIe DMA that I'm going to show at the end. Generated some new graphs. I was just mentioning that to Alberto. Since we got the statistics measurement stuff working, I can measure the latency of all the individual requests. So we have a plot of that at the end, which is going to be interesting to take a look at. All right, so the name of the game here in terms of the application block is to make it easier to customize the design. So the question is it possible to modify a part of the design without actually changing any of the core HDL code? And one thing I realized a while ago was that you can swap out entire modules. You just have to have the module name the same, with different file names. And then you can say, I want to use this Verilog file for the application section, or I want to use that one. And you don't need to change the actual code. You just need to change, the make file, or, the metadata associated with that. And this means that you could use, very easily add a new module and then use that on, whatever combination of boards that you want without having to modify each and every project. The way it's set up right, the current version of Corundum, or the legacy version of Corundum, you have to like make a copy of the whole code base and, make some pretty extensive modifications. But if we can compartmentalize this to adding a few modules without touching the core code, and then modifying, make files and TCL scripts instead of, modifying a bunch of Verilog, it's going to make it a lot easier to extend the functionality, to use that functionality on multiple targets instead of just one. And it's also going to make maintenance a lot simpler, because it decouples the, your custom logic from, the core logic in Corundum. So the I mentioned this briefly, but the idea is to have kind of a standardized module name with the standardized, set of ports and parameters, and then have a different file name. So for example, for the application, you might call the module MQNIC app block, and that'll have all the ports and the interfaces for interfacing with the data path. And then we'll have, kind of a MQNIC app block template.v, and then you can make a copy of that, MQNIC app block myapp.v, and then put your code in there. Now you can't change the module name, and every application block in the entire design is going to load your module instead of the default one. So you can't say, I want in one interface this application, and the other interface this other application. But it does allow you to swap this out, which is a rather useful capability. So that's kind of the goal with the application section, and then also with the scheduler to make it more reconfigurable. I'm going to kind of use this scheme. All right, so moving on to all of the various changes that I've been working on. The first one is making the control registers more flexible. So Corundum uses AXI Lite internally for all the register space. AXI Lite and using the AXI Lite crossbar interconnects and whatnot is nice for assigning large blocks of address space. But what if you want small blocks? What if I just want to add like one register? This doesn't work so well if you're using AXI Lite interconnects, because you have to, add another port, and you have a bunch of muxing and arbitration logic and whatnot. And generally, all the address decoding all has to be based on, powers of 2. So you can't just and it can't be overlapping. So I can't just, pass one register through. It becomes a real mess. So I did some thinking. I needed a way to pass or to assemble register spaces across multiple blocks, potentially even spanning hierarchy levels. So for example, all of the board specific code, we have a few control registers for controlling IO pins and interfacing with the optical modules and the board management electronics and whatnot. That sits kind of at the top level, and then inside of that we want to have the core logic, which actually implements all the control registers. So somehow we have to pass something up a hierarchy level in order to extend these registers. So I did some thinking, and I came up with an interface that I think is going to work pretty well for this. And the idea is you have an enable signal, an acknowledge signal, and then a wait signal, and then a timeout. So if you want to perform a register read or write, you can set the address and the data, and then set the enable high, and then you'll wait some number of clock cycles. I think the default right now is 4. And then I can have multiple modules looking at these signals, and you can set it up such that if one of these modules detects that, oh, that address corresponds to one of my registers, then it can either perform the operation and acknowledge it, or it can say, hold on a second, assert wait, do its internal computation, and then acknowledge. And then it will return the result. So with this setup, since we're not, passing around operations like you do for AXI Lite, and you have to make sure that, you return the correct result in the correct order and whatnot, it's much easier to extend this across, multiple modules and hierarchy levels. You don't need complicated mux and demux logic and things like that. And it's tolerant of a few pipeline registers here and there. It seems to work pretty well. And I've gone ahead and implemented this in 2 different places. One of them is in the kind of main register space for the control registers at the NIC level, so that those can be extended on each target board. And then I've also implemented this in the port logic, or sorry, at the interface level, so that gets passed through the ports for the port registers and scheduler control stuff. And it seems to be working pretty well so far, and it's nice and extensible. I also ported over the PTP clock subsystem. So instead of kind of piecing that together, I now have one nice little cohesive block where you can configure the number of period output channels that you want, and it'll automatically, figure out all of the register addressing and whatnot internally. So that seems to be working pretty well. So once I got that implemented, then I went and I added a block for the schedulers. So this is going to be kind of similar to how the application block works. You can swap out the entire scheduler by changing just the file list. I don't need to add, another Verilog parameter and then go drill down and say I want a round robin scheduler versus my custom scheduler. And then you got to go and add it to the generate block and yada, yada, yada. No, you just go edit the make file, point to the other scheduler block, and you're good to go. So it's very simple. If you wanted to make a custom scheduler, you just make a copy of like the existing round robin scheduler, delete the logic, and then implement your own thing. So this provides the necessary interfaces for that. There's a configuration and a control interface over AXI Lite. There's also a register interface that I didn't put on this slide here that uses the register interface I just talked about for implementing a couple of control registers. And then there's the scheduler interface, which is a doorbell from the NIC data path, TX request to the NIC data path, and then the TX status that comes back in response to the request. And then there's also some additional interfaces, specifically PTP time is provided to the scheduler in case you want to do some sort of scheduling that's dependent on the PTP time. So this is implemented for all the targets already. And like I said, I have 2 blocks available right now, the standard round robin scheduler and the TDMA scheduler block. So eventually what's going to happen is if you look in the repository, there's 2 kind of folders. There's the MQNIC folder, there's MQNIC TDMA. Well, the MQNIC TDMA is going to go away eventually once the TCL configuration is applied for all the targets. And then you can run the TDMA scheduler on any target just by changing the make file and the settings in the TCL script. All right, so that's a scheduler block. Then I also went and I reorganized the address space a little bit. So I took the port registers that previously were sitting inside of kind of the port address space. So the port registers are really small. The port address space, we provided a lot of space for the schedulers, because the schedulers you're going to have to access, on per queue state, basically. So that takes up a lot of address space. But the control registers, there's just a couple of them. So the original implementation, it basically cut that address space in half. The first half was the port registers and the other half was a scheduler, which is highly inefficient. So what I ended up doing is moving the port registers through this new register interface setup into the address space of the NIC interface. And that frees up that entire address space that we had allocated for the port for schedulers. And the great thing is I didn't have to change a driver to do this because of the way all of the kind of indirect addressing works in Corundum. I had to do some kind of funky computation to get the offset right, but it does work. And all of the designs, I updated the standard port module to do this. So all the designs benefit from this already. And eventually what I want to do is reorganize the register space a little bit more to normalize all the offsets, and also to move a few of the port registers into the interface. But that's probably going to wait until we do the shared interface data path, where basically most of the port registers are going away because all of that logic is moving into the interface. All right. And then that brings us to the shared core logic. So I mentioned this a couple times before, the idea is to simplify the maintenance by reducing duplication inside of the the core logic in Corundum. Reduce duplication across all the target designs by integrating all of that into one set of core registers. So the idea is something like this. We have MQNIC core, which doesn't have the DMA engines, but it has all the interface instances, all of the DMA infrastructure interconnections and whatnot, all of those muxes. And also has the FIFOs. I moved the async FIFOs into this module as well. And then what we can do is we can wrap that with the DMA engines. So we have MQNIC core PCIe, which adds the PCI Express DMA modules and the PCI Express AXI Lite master modules. And then we could also make one for AXI. So if you wanted to run this on an SoC or whatever, then we can have MQNIC core AXI, which instead of having the PCIe DMA has the AXI DMA modules. And then you can just drop that on the Zinc and and get up and running. And then inside of well, I guess not really inside, but we can add additional modules. So for ultra-scale devices, we then have MQNIC core PCIe ultra-scale, and that adds the ultra-scale interface shim, which takes the new generic PCI Express interface and adapts it to the RQ, CQ, CC RC interfaces that that the ultra-scale devices have. So I've got this working on the Silicom FPGA board for now, validated in hardware. It works. I've also converted the U280 just so I can get all the placement constraints correct. Eventually, once I get a couple of these other features hammered out, then I will go ahead and port all the designs. But kind of in the interests of sanity for the time being, I'm only going to port one, get the kinks worked out of that, and get some of these other components implemented, and then just port everything in one shot. So yeah, I have made a couple of changes that were kind of departing from how things are currently designed. One of the changes that I made is that I've also pulled the asynchronous FIFOs inside of the core logic. And this is done for a couple of different reasons. But let's see. So one of the reasons for doing this is then you can provide, if you want, the direct MAC connection to the application block if you want. So if you're trying to do something really low latency and you want to, connect directly at the MAC interface, you can do that. And if that was outside, then that would be more difficult. The other reason for doing that is eventually what we're going to have to do with the shared interface data path is have a big, shared TX and shared RxQ module, which kind of does data width adaptation and a few other things and handles, PFC pause frames and whatnot. And all that's going to be synchronous. So we need to have a separate large synchronous FIFO and small asynchronous FIFO. So by putting all of that in the shared logic, it means I can, do all that shuffling and whatnot, change all those settings all in one place instead of having this kind of strewn across the hierarchy. And that's another change that I made as well, is that I have, instead of a single large async FIFO, I have a large synchronous FIFO and then a small asynchronous FIFO for both the TX and RX direction. And this means that for the ultra scale devices, the large FIFO can now use ultra RAM, which saves some block RAM, which is potentially useful if you need to use block RAM for the application, because the ultra RAM modules they support dual clocks, or they support dual ports, but they're not dual clock, whereas the block RAMs are actually dual clock. All right, so that's the shared core logic. And then I'm also taking all of the top level Verilog parameters and pulling them up all the way through the top level Verilog file, and then adding a TCL script that you can use to change those parameters from Vivado. So in this way, if you want to, change, the number of interfaces, the number of ports, the number of hues, you don't need to change the Verilog. You can just change the TCL script, and that those settings will get propagated down into the design. And this is particularly important when you want to customize a design by, inserting your own application logic. Well, you might also want to change, the number of ports or, the number of queues or whatever. It kind of defeats the purpose of being able to swap out the application block if you have to edit the Verilog anyway to change some of these parameters. So by pulling them out into a TCL script, then, it makes things a little bit more flexible. The other cool thing about TCL is all of the IP core settings are also done by a TCL. So what we can do is actually take like the PCI Express bar size parameter, and we can set that both in the Verilog design and in the PCI Express IP core settings. So if you change the bar size, you don't actually need to go digging through the PCI Express IP core configuration to make sure it's all synced up properly. The configuration script will take care of that. So this is currently implemented again just for the Silicon board, but eventually, once I get things a little bit more fleshed out, I'll port it across all of the target designs. All right, so one other thing that I wanted to get squared away before getting the application section integrated was the statistics counting subsystem. So I figured if we're going to implement statistics, we should do this properly instead of just implementing a bunch of 32 or 64-bit counters, willy-nilly all over the place. Have something a little bit more centralized. Because if you want to implement like 164-bit counters, that's a lot of flip-flops to do that. And then you also have to have all of the logic to, merge all of that together so you can access it via AXI Lite or whatever. And it's kind of a pain. I mean, it works, but it's kind of a pain. So what I ended up doing is aggregating a bunch of statistics counts in blockgram. So there's kind of two main modules that are responsible for this. One of them is the statistics counter module. And the idea with this is it receives updates to the statistics counters via AXI Lite, and then it sums that into a blockgram instance, and then you can read those counts out via AXI Lite. So Corundum is going to have one of those modules kind of sitting at the NIC level, and it's going to collect PCI Express statistics and statistics from the Ethernet MACs and from the data paths and everything. And I think we can support pretty easily a few thousand statistics counters if need be. So we got the stats counter, and then we have the stats collector, and this component it receives either strobe inputs where you have a single cycle pulse to increment the counter, or increment inputs where you might have packet length or something. You show the packet length for one clock cycle, and then it aggregates it. So what this does is it takes those inputs and it aggregates those into a distributed RAM block, and then periodically it will dump the counters out of that distributed RAM block via AXI stream for the statistics counter module to collect those. So I also have a few modules that kind of wrap the stats collect module and connect that up to PCI Express TLPs or the DMA engine or whatever. And right now, kind of the current status is that the core logic is integrated into the new shared logic, and we have the PCI Express and DMA statistics collection implemented. Right, so for PCI Express, just a little overview of what we can collect. For PCI Express, we're basically collecting a bunch of traffic stats. So, counts for memory read, memory write, IO, configuration, message, completion, and atomic TLPs, error counts, poison TLPs, UR and CA completions, and then, DWORD counts for the header, request, payload, and completion. So from this, you can get an idea of, what kind of traffic is going over PCI Express. And then on the DMA side, there's several different things that we can collect. So we have there's kind of two different categories. There's operations and requests. So operations are when the user logic asks the DMA module to do something, that's an operation. But one operation could issue multiple requests over PCI Express because those requests are going to be limited in size or whatever. So we count the number of operations, we count the size of those operations, and we also compute the latency. So I have a module which it looks at tags coming from the PCI Express DMA engine to determine when each operation starts and when it terminates, and then it'll report how long each operation took. So from that, you can compute kind of the average latency of various operations. And ostensibly, it'd be possible to divide this up a little bit to maybe build some sort of a latency histogram or something. Right now, it just adds it up. It also computes some error counts, so timeout and error counts, and then some flow control information. So if you run out of tags, it increments a counter for that. If you run out of transmit credits, it increments a counter for that. There's also a limitation on the number of kind of in-flight operations in the transmit pipe. So if you hit that, then there's a counter for that. And then if you get back pressure from the IP core, then there's a counter from that. So hopefully using all of this, we'll be able to get an idea of, what's going on the PCI Express side, and, if there's changes that need to be made to, improve the performance. So yeah, like I said, this has been implemented, in the repository right now, and it's been integrated into the core logic. And that means the next step is to actually bring up the application block. Right, so the application block, the idea is that you can implement your own custom logic, and you can swap that in just by changing the file list. And this provides, kind of all the necessary interfaces to the core data path and logic. And so part of this is, configuration and control over AXI Lite, we're going to have a PCI Express bar that's dedicated to the application block. And then the application block will also have access to, the core data path for the NIC. So if you want to, change scheduler settings or something else, you'll be able to do that. And then we have streaming data interfaces for, the Mac interface. And then also eventually we're going to have a separate internal interface that's going to be connected, on the far side of the internal FIFOs. And then we have the connections to the DMA subsystem. So you can perform, DMA read and write operations from the application section. We're going to have connections to PTP time. Eventually, there's going to be potentially a bunch of flow control stuff that has kind of yet to be determined at this point. But yeah, I'm working on this right now, getting some of these parameters kind of hammered out and getting things connected up into the core logic. And what I'm going to do is provide, a blank template module, which basically kind of ties off and terminates all the connections. So you can go in and, remove that for the connections that you want to use and, wire up your custom logic. Then I also realized that I can very easily run basically the DMA benchmarking design that we put together separately in the application block. So that'll be kind of a useful feature. You can drop that on there. You can run Corundum and you can run kind of the DMA benchmark in system just to get an idea how that's going to work. All right, and just for a brief overview of kind of how the workflow is going to work. If you want to implement some custom logic, the idea is that you can go in and you can make a copy of the template application block module. So you'll rename that based on your application. You'll add, your custom HDL in there. And then if you want to test it, what you can do is either find the, shared core logic test bench or a test bench for one of the target designs, make a copy of that, which is it's like a make file and a Python file. Pretty simple. And then you edit the file list to point it to your application block and any of the code that you need. And then you run make to simulate it. Simple. And then if you want to, run your application logic on a particular FPGA board, if it's already supported, it's easy. You just go into the target design and then you make a copy of the build directory, which it just has two files in it, right? A make file and a config.tcl script. You hit the make file to point at your Verilog files, and then you change the settings as appropriate in the config script, and then you run make to build it. Piece of cake. Now, this doesn't say anything about what's going on the kernel module side. That I'm going to have to sort out at some point, but I'm going to get the hardware side of things working first. But the idea is that you shouldn't need to edit, any of the core Verilog code for Corundum. You just need to add, your code in the application block and then point, the Corundum build setup at that, and then you'll be good to go. And if you've already modified Corundum for something, I guess either you're going to have to keep working on your fork of it or, pull that logic into, an application block and then use that. So unfortunately, if that's the case, I apologize for making you do extra work, but in the long term, this is going to be a much more flexible solution. All right. And then once the application section looks good from my point of view, then I'm going to go ahead and port all the designs. So I'm holding off on doing that for now, just for reasons of my sanity, having to make all these minor changes to all the different designs. I might as well make it on just a small number until I get all of the kinks worked out and then port them all in one shot. And as soon as the application block is looking pretty good, then I'll go ahead and pull the trigger on that. Right. So that's kind of the status update in terms of what the designs are looking like and where we're going in the future for the core logic. The other thing I'm going to talk about briefly is a little bit of benchmarking that we did on the PCI Express side of things. So this was kind of catalyzed by some stuff that Alberto was working on. I've been meaning to kind of put together some sort of an isolated benchmark design for PCI Express for a while, just because, with something like that, then we can run the DMA modules in isolation and get an idea of, where performance bottlenecks might be and what kind of achievable performance you can get on, on a given system. it would be great if as part of the Corundum kernel module loading, it would run a couple of very basic benchmarks and then report, here's the achievable bandwidth, just so you can get an idea. Well, if your link rate is only hitting 50 gigabits per second, well, then you can go look at the output of the device driver and go, oh, the DMA benchmark only ran at 50 gig. There must be something wrong with my machine. um, so yeah, that kind of stuff would be useful, but it would also be useful to have a kind of more comprehensive benchmark suite, so we can try different sizes of data, different access patterns and whatnot, just to make sure that it's working as we expect it to operate. So I put together a relatively basic benchmarking design where you can run a whole bunch of reads or writes, and you can adjust the block size and you can adjust the stride. And the initial measurements that we did were somewhat interesting, actually. So I got a couple of graphs. All right. So the first test we ran, super simple. We did 10,000 block reads per size for a bunch of sizes between 1 and 8192 bytes. Right. So we did 1, 2, 4, 8, so on and so forth. In this case, we did the side equal to the stride. So we would read one byte and then we'd read the next byte and then read the next byte. No gaps, and we're not reading the same memory location over and over again. And to compute the throughput, we measure the overall time. So basically, we have a stopwatch in the FPGA. We would start that when we issue the first operation and then stop it when the last operation completes. Relatively simple. As expected, the rates monotonically increase with size, and it saturates at 256 bytes. That sanity check checked out. But then we noticed something interesting. If you don't scale by the data rate, the time did not increase monotonically. That was really interesting. So here I have the time plotted on a log-log plot. Interestingly enough, the transfer time decreased from 1 byte to 64 bytes, and then it increased again. Second part is, that makes sense. But the first part, what the heck is going on there?
And
to be honest,
you're not dividing this by size, right?
I'm not designing that by size. Yeah, it's just the time it takes to transfer all of the blocks.
And by however.
Right. So yeah. So for every test, we did 10,000 blocks. Right. So ostensibly, you're going to be transferring more and more data, for each one of the tests. Oh yeah. Okay. So on the transfer size, I guess I should edit that to block size. But yeah. So yeah. So if you want to multiply the bottom one by 10,000, whatever.
Just curious, does DDIO enabled in this benchmark?
DDIO
memory or L3 cache?
Yeah, in this case, we weren't doing any kind of DDIO. This is just like, let's just see what happens here. So yeah, that's definitely something that we might need to look into to see, if we can change the performance at all.
Of MMIO, something like that.
MMIO?
Yeah.
Well, this is only DMA. This is the card is doing everything here.
Okay.
And you're showing the read or the write plots?
This is read. I mean, so the really interesting thing is we were seeing this for both read and for write, which was really perplexing. So whatever's going on here, I mean, so the hypothesis that I have is that from the PCI Express side, we're not hitting CPU cache. We're probably going straight out to DRAM. And therein lies the problem, because if we're hitting, the same 64 bytes, it's possible that the memory controller is, for instance, always doing a 64 byte read every time you perform any operation. And if you hit the same block of 64 bytes multiple times, it could be reading that block multiple times from the DRAM. And I know with DRAM, if your memory access pattern is not great, you can run into some, long delays in terms of having to close out a row and then reopen it instead of opening a different row, where you get some benefit to parallelization. So we could be running into something like that, where it's completely uncached and we're hitting the DRAM multiple times. That's my hypothesis so far. Now, there may be ways we can improve this, with DDIO or whatever. That's certainly something that we can look at. And this is why we benchmark stuff, right? Once we kind of, that's certainly something that we can take a look at. So I was thinking maybe this had something to do with cache lines, not sure. So we did another experiment, And what we did is, again, we did 10,000 block reads, this time all of 1 byte. And we adjusted the stride from 1 byte up to 256 bytes. So, read 1, read the next was stride 1, read 1, skip 1, read 1, skip 1 was stride 2, read 1, skip 3, read 1, skip 3, so on and so forth. And the transfer time decreases from 1 byte up to 64 bytes. And at 64 bytes, it flatlines because, apparently you're not running into the same effect when you're hitting different blocks of 64 bytes. So this definitely indicates there's something not really with the 64 byte, size, but with these kind of 64 byte blocks in the address space. As for exactly what that is, I'm not sure. We have some hypotheses, like I said, but yeah, not sure. This is just more of a measurement thing at this point. And then what we can also do is take a look at the data transfer rate. As you would expect, as you're changing the stride, it goes up. Why would the throughput be dependent on stride so much? But that's what we're seeing. And then more recently, I got the latency measurement working for the PCI Express DMA subsystem. So originally, when we took these measurements, we were just looking at the overall time it took to take the transfer. But now that I have all these statistics counters for the latency, we can take we can run this experiment again, and we can measure the latency. So this is how long it takes between, for every operation over PCI Express. When we issue the read request, we start a stopwatch, and when the completion comes back, we stop it. And we have a whole table of these stopwatches, basically, one for every PCI Express tag. And using that, we can measure the latency of every single read request that gets issued. So we ran the exact same measurement. This is going back to the first one where we have, stride of the transfer size, and we ran from 1 to 8192 bytes, and we measure the time between when the read request is issued and when the last completion comes back. So if we run out of tags, that doesn't affect the latency measurement here because we won't issue the read request until, there are tags available. And we get this minimum at 64 bytes. And this is just a huge drop off. You'll see here that the latency for 1 byte operations is higher than the latency for 512 byte operations.
And really you're saying that this is basically the time that it takes to close and reopen, whereas when you have several, your read is wide enough that's going to eat several 64 chunks. It's almost faster to read those 2,
right.
3, 4, 64
like,
chunks.
It seems to me that if you're going to be touching the same 64 bytes in memory more than once, you might as well just read the whole thing once.
Yeah.
There's the overhead apparently of going through the memory controller and reading it twice is way higher, even more so than just PCI Express overheads of just reading it in one shot. So this is also kind of one of the motivators behind the variable length descriptor support, because right now Corundum reads all the descriptors individually and there's 16 bytes. So yeah, I guess you have 4 of those inside of each 64 byte block. So you read that 4 times and you're going to suffer that multiple read penalty that we're seeing here. So with the variable length descriptor support, we'll read one big block that will have, it could be 256 or 512 bytes or something. We'll have multiple descriptors, and then those can just be returned from, block RAM cache basically on the FPGA. So yeah, that should produce a performance improvement, hopefully, once I get that working. So after the core data path and logic and whatnot, that's all done, then I can work on the variable length descriptors, and this is more motivation for why that's a good idea. And then we can also run the same latency benchmark for the single byte operation case, and we see literally the exact same plot as when we measure the time. Like, look at this. Look at that. We're just changing the scale. The curve is exactly the same, which is interesting because this plot where you're measuring the time actually does take into consideration the fact that we're running out of tags and whatnot, and we have to wait for more tags to be available. Whereas this one is only looking at the latency of each individual operation. So I'm not exactly sure what's going on there, why we're seeing exactly the same curve, but I guess the waiting around for tags must average out. Anyway, that about rounds it out for the slides that I have here. And some interesting figures. I mean, what do you think of that latency curve, Alberto? That's definitely good for the paper that
Well,
we're
it
putting
makes,
together, right?
yeah, it makes the case quite interesting. So I was reading the RPMEM 2.0 slides of the protocol that we uncovered, you know, a few days ago, and I'm just wondering, they make it clear that you can actually route this request inside the CPU to one memory controller, to the other memory controller, to the actual caches. Yeah, it would be interesting to see if we can pull these things off of the caches on purpose.
Yeah,
It seems to me that if we don't do anything, this is our, and I may not get the terminology right, but these are non-allocating operations.
right. Yeah, I guess that's one thing I should mention is that we ran these tests twice. Once with memory allocated by the kernel using the DMA alloc coherent call, and once using just the standard page allocator, and then, you know, memory mapping that for DMA, once for read and once for write. So yeah, and we saw similar behavior for both. It wasn't quite the same, but it was, you know, and if you looked at the raw data, you were getting slightly different numbers, but the, you know, the overall kind of trends were the same. So yeah, not quite sure what was going on with that. Oh, the other thing I will mention as well is that we ran this on 2 different CPUs. So all of these measurements were taken on an AMD EPYC Zen 2 CPU. And I also ran it on an Intel 6138 CPU, Intel Xeon 6138. And on the AMD one, we saw, you know, this kind of similar throughput issue with reads and with writes, but with the Intel CPU, we didn't see it with the writes. So it looks like the Intel CPUs are doing some sort of coalescing before actually sending it out to the memory, whereas the AMD ones are not. Not exactly sure what's going on there, but it was an interesting difference. But we were seeing similar behavior on the read side. Obviously, the exact numbers were a little bit different, but same kind of thing, where smaller operations were taking longer than larger operations. So yeah, now that we have the benchmarking stuff working, it would definitely be useful to, you know, hammer on this some more and, you know, try some different approaches on the software side in terms of, you know, can we use DDIO or, you know, whatever, and see what that does.
And you think that this could be controlled by the hint bits that we spoke about?
We'll see.
Still not sure.
Maybe,
Yeah.
maybe. I'm not super familiar with DDIO and whatnot, so I'm going to have to get up to speed with that. And then, you know, if I need to make some modifications to the DMA engine to support that, then that's what we got to do, right? Because if that's going to be useful for the NIC or for, you know, for application logic that might be running on there, you know, that's definitely going to be worth it. And I should probably also flip the switch on the DMA benchmark repository to make that one public, because that we ended up not doing anything weird in there.
I thought DDIO, whether DDIO is enabled is determined by the CPU architecture.
I mean, I think it's a combination of things. So we found a little presentation that talked about that a little bit, and there's a bunch of registers associated with that are CPU specific, but then there's also some bits in the TLP header, some not the transaction processing hits, the ATTR bits. I think specifically the no snoop bit is the one that you need to play with, and I can't remember if it needs to be set or clear, but yeah. So I think you can kind of control on a per operation basis whether an operation will be, you know, sent via DDIO based on those bits. mean, obviously,
Oh.
there's other platform specific stuff as well, but that's
And by the way, people
from
need
the
that.
device end, that seems to be kind of the only thing you need to do.
People need that to implement some sort of RDMA flush, which has been discussed for a while now.
Actually, this reminds me something like recently many papers discuss DDIO has a negative effect to the network because DDIO is write allocate. So if you always write something to L3 cache, you may end up evict some hot data already in the L3 cache. So if we can control whether the data is write to L3 cache or memory, we can do something here, right?
Right. So that's what the no snoop bit does, right? So I think, so if you want to use DDIO, there's kind of two parts to it. One of them is getting the CPU and the system set up, to support that on the host side. And then the other one is on the device. You can set or clear the no snoop bit, which determines whether or not it's going to allocate into the cache on a per request basis. So the point I was trying to make is that, if we have to, thread that bit through the DMA engine so you can adjust it, then that's what we got to do.
I mean, here is a interesting research problem, like related to the network performance. Anyway.
That paper was very good, by the way. They figured out a bunch of registers to, I think, determine associativity on the DDIO area, the size of the DDIO area that you want to dedicate. They did pretty good reverse engineering in that one. I think this is the one we're talking about, right? Last year on Usenix. Or this year, something relatively recent.
Well, you can certainly pop that in the Slack channel, and then we can discuss it.
Hello, I have one question.
Sure.
Have you ever tried playing with TPH and steering tags? Does it affect the latency performance of the DMA?
We have not tried that yet. That would be an interesting experiment. So I'm actually not sure how much support there is for the TPH and steering tags through the Xilinx PCIe IP core. I know they do it in a non-standard way, so I have to take a look at that in terms of actually implementing that. I've done nothing with that, but that definitely could be something worth looking at. I also don't know all that much about how it works exactly. It's like I've looked at the TLP formats, right? I know where the bits are in the formats, but beyond that, got some reading to do.
I also have no idea how steering tags work because I couldn't find any place in the document where it explains how exactly they work. They just say where you can locate the table, but it doesn't say anything about the contents of the table, or I couldn't find. Maybe there is something, but.
So you're looking at the PCI Express specification, or?
Yes, PCI Express specification.
Gen 3, Gen 4?
I just checked Gen 3, 3.0, but I haven't checked any recent version of it.
Okay. I mean, it's possible for some of the stuff, they kind of leave it up to the, system implementer, like PCI Express gives you this capability. But what you do with that is then dependent on the system that it's installed in. So you might need to look more at potentially Intel CPU documentation or whatever to figure out exactly what's being done with that information.
Thank you.
But yeah, if that's something interesting, we could certainly thread that through the DMA infrastructure as well. So you can add steering tags and whatnot. I think part of the problem is that right now the PCI Express simulation framework I have doesn't support TLP prefixes. So I need to take a look at whether that uses a prefix or not. Actually, for the TPH, it may be inserting that into the payload somewhere. I need to look into that. at any rate, the framework that I have right now in Python doesn't support that yet, because you have to make some. It's either using a TLP prefix, which is not supported yet, or it's recycling some internal fields, which is also not supported. So yeah, we'll have to take a look at that. But yeah, now that we have the benchmarking design, that would be a good platform for experimenting with some of this stuff. Let me see if I can make that repository public real quick. I'm not sure if anybody else has any other questions or anything.
Just a quick comment on the stats.
Sure.
It'd be nice to pull them off of the card at some point.
Pull them off of the card?
Yeah.
What do you mean pull them off of the card?
Let's say you have a card with 2 ports. You could be like streaming them somewhere, so you don't get the aggregates, but you get the instantaneous as well. You can reconstruct interesting, can find interesting events if you look at the time series. I mean, this is
so
really,
okay. So you're not talking the individual updates, but kind of read the counters at a higher frequency, right?
You wouldn't be able to stream the individual updates depending on exactly which counter you're looking at. Yes, but yeah, more frequent snapshots would approximate that. I don't have a case in mind, but the thing is, it's interesting to be able to take instantaneous frequent snapshots of it.
Let me show you guys something real quick here. This is a real quick and dirty tool that I put together that queries the statistics subsystem on Corundum. I'm not sure if you guys can see that, but here are all of the performance counters that are currently implemented. It's querying them once per second, and then I can run iperf, and we can see the counters responding. So with this, you'd be able to read at, I mean, a reasonable rate. You could read, probably every millisecond if you really wanted to. And, read out what's going on in the counters. In terms of, reading these things more often than that, maybe you would have to do that on the FPGA from some other block or something. Not sure what would make the most sense, but it is definitely possible to read these, at even probably a pretty high rate from the host. I think right now the kind of statistics update takes place I think around every 4 microseconds or something like that. That's how often the counters get dumped out to the aggregated, to the block RAM. So you won't be able to, with the current setup, look at it any closer than that. But if you want to do something special, what you could do is, pre-process stuff. If you want to build a histogram of, latency or something, then you can modify the Verilog to collect that and either return it some other way or, add some new counters, just for that measurement or something. So.
Got it. Thank you.
All right. Let's see. Anything else to discuss for today? I think that drowns out everything that I wanted to talk about. At some point, we definitely need to get the ball rolling on RDMA some more. The main priority on my end is getting the application section and whatnot all set up. So once that's done, then I'm not sure how much time I'll have to work on RDMA, but I know Alberto, you wanted to help out with some of that, but you're also working on some papers on your end. So
I think the interesting thing is those 2 things could be on the same critical path. So I'm gonna have to do something about it at some point. We have a little bit of a ramp up with the code base to do, so it's not, we're not gonna see immediate results, but yeah, we wanted to, but I think looking at those micro benchmark aspects of DMA is already doing it. It's not the same code path that you want to do, but those experiments will kind of inform how we may want to implement.
Definitely,
things.
definitely.
So this is very useful.
Anyway, that's the DMA benchmarking repository. If people want to take a look at that. It currently supports just a couple of boards. If it's pretty easy to port to another board. If somebody wants to use that on a different board, let me know. I'll add it. It's not that big of a deal. Yeah, it's like I'm using mainly that Silicon board on my end because it's a small FPGA. It builds quick, and then but I also have support for the U50 in that repository. So all right, I guess it's been an hour now. I guess we're at time. If nobody else has any questions, then I think we'll close it out for this week.
Oh, by the way, Alex, are you going to share the slides?
Yeah. I've been putting all the slides up on the Google Drive afterwards. So yeah.
Oh, this is great. Actually, what I am working on is a project that's related with the NIC DMA performance. So we are trying to improve the NIC DMA pipeline efficiency, something very related with this. So I believe the DMA benchmark you provide can give a great help to us.
Sure. Yeah, let me know what FPGA board you guys want to run it on. If it's not already supported, I'll add it. If it's something that's already supported in Corundum, I'll port it over. It just takes a few minutes.
Oh, yeah. So does this has a specific FPGA? It only support it only supports a specific FPGA?
No, it should run on any Xilinx Ultrascale
Okay.
Plus or potentially 7 series device.
Yeah.
At least for right now.
Okay.
So yeah, I just want to. So you could port it to whatever device you have, or I can just do it because I can just copy stuff over from Corundum or whatever, and then make sure it's all, organized in the repository and working and whatnot, and test it on my end, so you have something that is going to work. All right. Well, if nobody else has any questions or comments, then I think we'll go ahead and close this out. See you guys next week, or in 2 weeks.
In 2 weeks. Thank you.
Thank you.
Thank you.
And thanks to all you guys for tuning in.
Thanks. Bye.
Talk to you.